This afternoon session is Patrick Thiran from Lausanne.
Thank you. Thank you very much. Thank you for the organizers for having set up such a beautiful program and for inviting me to take part in it. So today, for the last talk, I would like to mention some work we have done using, so I'm not going to present you new mathematical results on random graphs or spatial models, but rather how we use them for some networking problem. And so I'm going to present that. This is joint work actually with Olivier Douce, who is here as well and who contributed a lot together with Mathilde Durvy to the first part of the talk, as well as to Adel Aziz and David Staroblisky for the second part of the talk. So what I'm going to talk about today is medium access control algorithm for multi-hop wireless network. So let me introduce a little bit the two scenarios I will consider here. The first one, so in all scenarios we have a number of nodes which communicate with each other via wireless link via wireless links in multi-hop fashion, as Piyush explained this morning. And in the first scenario, I'm going to consider here, instead of looking at capacity, I'm going to look more at medium access control, so how scheduling decisions are made to transmit these packets from one node to the other. So it's different from the previous talk. And I'm going to consider first the case in which all the nodes are saturated. So they all have an infinite backlog of packets to transmit. And so that simplifies a lot of things, because in this case, for example, I don't need to consider traffic matrices. I don't need to consider delay. Essentially, what happens in such a network is that when a node, for example, this one, wants to transmit a packet to one of its two neighbors to which it is connected, well, for example, to the right one, he will need to send some control messages, or this node will discover that the transmission will need to take place by a carrier sensing mechanism, and it will refrain from transmitting any packet during the transmission of this packet. Likewise, the right neighbor here of the destination will be informed, I will explain in a moment how, by this node that the transmission is taking place and should refrain from transmitting any packet. Why is that? Because if these two nodes were engaging in the transmission simultaneously, well, I would have a collision due to interferences, and the transmission would not succeed. So the way we are going to view that is that each of these transmission takes a footprint. So whenever I have a transmission here, essentially I have an interval here of 3 hops, which is consumed by this transmission. And so what will be the goal? Well, the goal will be to maximize throughput, as this morning, but here, more precisely in this scenario, the throughput simply boils down to maximizing, to packing as many transmissions as possible on a network. And so we want the network to reach a high level of spatial reuse this way. We do not consider delay, because anyway we have infinite queues here, so we drop that aspect. And the second aspect we would like to have is that not only we use the wireless resources as well as possible, but also we gave to each of these nodes an equal fair access to the channel. And so we are going to look at fairness. Here what fairness means essentially is that the proportion of time that each of these links is indeed transmitting is roughly uniformly distributed around the different links. And as we're going to see is that in 2 dimensions, well, we have a phase transition that affects critically fairness and spatial reuse. And we are going to explore this trade-off. In the second part of the talk, I'm going to consider only one node, which I will consider to be the source, as infinitely backlogged. And all the other nodes initially do not have any fresh traffic. They are only relay, with the last node being the destinations. And so here, the question will be that we want to transmit packets from one end to the network to the other end of the network. So what I'm going to look at is not really the spatial reuse, but the end-to-end throughput of the network. And there I will consider delay. I would like that the network is stable. In other words, that all the queues here of all the nodes but the source, of course, be almost surely finite. And so that's what we are going to do later on. Okay, so let me give a little bit my own view of the state of the art. Is that there is a lot of work on this area, and because it's very complex and very subtle effects matter considerably in these kind of networks, and so it's very difficult to distinguish them, and so there is a lot of work. Single hop networks are much clearer, so there are models which are well accepted by the community, which actually can be made quite rigorous, but multi-hop networks is definitely very difficult. And you can criticize all the models, including the ones I will present here quite strongly. First, because they apply to particular scenarios only. Typically, we have only two hops, or we have line networks, as I will only often present here, with a particular traffic matrix. They rely on hidden assumptions and so on. So they all have this weakness. Or they are extremely complex. They are so complex that essentially they boil down to a high-level simulation, but they gave very little insight. And finally, they can be simple, but made very strong explicit assumptions, so not only in particular scenario, but also in the model, such as, for example, a time-discrete model, continuous back-off distribution, as we're going to make here as well. So we cannot draw final conclusions for the model at all, and I think for quite some time, but much progress has been made, and there is really a lot of work done, especially in the recent year, both in the saturated case and the non-saturated case. I can cite only some papers in both cases here. So here, what I'm going to present is actually a loss network model of CSMA. We are going to hear about other models for medium access control, which look more at how the geometry, the interaction between medium access control and geometry with Bartek, I think, later on during this workshop. In the non-saturated case, well, from the seminal work on back pressure by Leandro Stasioulas, essentially you have schemes that rely on message passing between nodes to coordinate and transmit their packets. And more recently, there is a big wave of work for distributed schemes without message passing, but still using CSMA, avoiding to have nodes exchanging messages before they can actually send their packets, of course, is a considerable advantage in practice. And so ideally, what we would like to look for, and that's a little bit the perspective we like, is of course to have decentralized algorithm that do not require message passing. I think now for the last 2 or 3 years, the community is more and more convinced that actually we should not need this message passing. In practice, it makes a big difference. Otherwise, of course, if we find implementations that are efficient with message passing, that could definitely change the picture. That do not require to estimate the capacity of the wireless channel. Why is that? Because in contrary to wired network, in which the capacity is something which is very, very static and well known, in wireless network it fluctuates a lot and it's very difficult to estimate. So if you rely on the precise value of the capacity of the wireless channel, it might be difficult to implement in practice as well. We would like to use hardware off the shelf. Just because if it's possible to use components that we have, well, we can experiment that right now. And we would like, if possible, to be as transparent, I would say, to layers such as IP, TCP, UDP, so to have something which has as few changes as possible so that we can deploy it without having to change anything else. So these are some of the constraints we have. Now, let us begin the first case. So let me explain the model at the same time as I explain the protocol. So what I will take is an idealized version of CSMA, so in which I don't have any collision. I'll explain in a moment how that is implemented. And essentially there are two parameters I will use throughout the talk here. One is the average transmission time or exchange time would be more precise because there are packets actually flowing between source and destination, so we'll call it exchange time. And the other parameters is the back-off duration. It's a protocol that works with back-off. The average backoff is of duration 1 over lambda, and it works as follows. So imagine that I have these two nodes here who would like to transmit a packet to each other. Actually, these two nodes will draw a random value here, a random variable, which will take as exponentially distributed. That's the first approximation, a very strong approximation that we make compared to the real 802.11 protocol of duration 1 over lambda, and the shortest one will have then the right to transmit when its timer expires. Then the transmission takes place. It lasts for an average of 1 over mu. In this case, this node will receive the packet, and these two nodes will be, because of the carrier sensing mechanism, inhibited from transmitting throughout the duration of this packet. So the remaining backoff value is frozen. It's reported at the end of the transmission. And the nodes which has just finished redraws a new backoff value, and the processes is ready to continue. This time is the first one who wins, and so on and so on. So that's the simple mechanism that takes place. Now, how that is implemented, in principle, actually, there is a set of handshakes taking place between source and destination. The source indicates first by a request to send to the destination that it is willing to transmit a packet. The request to send has for effect that all the nodes within the receiving range of the transmitter are informed that the transmission will take place. And so this way, know that they should refrain from transmitting during the transmission of these packets. Likewise, the destination, if it is not inhibited by another concurrent transmission, replies by a clear to send, that it is free to receive a packet, and this is again heard by all the nodes within the receiving range from the destination. And once this is done, this handshake has been done, all the nodes that are involved in the transmission, as well as all the nodes which are in the interference range with the transmission, know whether they should transmit or not, and so no collision can take place from that point on. So we'll take only that view. There are, of course, the picture is much more complex than that, but just that view of the model. So then the data can be transferred, and that's the part which takes a lot of place. The approximation that we make is that this is instantaneous. So the RTS, CTS are short packets, and we'll come back later on these assumptions, but from now on, we assume that carrier sense is instantaneous, and so time is spent in the transfer of the data. So once we have that kind of simple model, you can see that active and idle link form an independent set of the contention graphs, or the inference graph of the network, and essentially you can view that simply as a packing problem. To each active links you associate on the line an interval of length L. Here I will speak only of length 3, and intervals come as a Poisson process because the backoff are simply exponential ID random variable and leave after a time equal of 1 over mu. And so we'll take, for simplicity again, also exponential distributed time. Once you have seen that, well, you have seen that actually this is a model which is very well known, especially here. It's a loss network, and so it has a very nice product solution that we can explicit as follows, simply as a function of the 2-parameter lambda over mu. And so once you have that, well, you can compute a number of things. So the two metrics of interest for us, first is the spatial reuse. So what is the average proportion of links that are active in the network? And the second one is the fairness. How far are we from a distribution of the active links which is uniform? And the metric which is used is a fairness index, which is a number smaller than 1, which expresses actually how far we are from a uniform distribution of the probability. So that's the Jane's fairness index, which is the most used to it. So the closer we are to 1, the closer we are to a uniform and a perfectly fair situation between the different links. The smaller this fairness index, the more unfair the situation. Now we can compute explicitly on the line many things. So for example, on the infinite network, you can compute the spatial reuse. And the spatial reuse, if you vary the spatial reuse as a function of lambda over mu, you can see that it increases, and actually it increases and will tend to 1/3 on this line. That's the maximal spatial reuse you can have, because each active transmission consumes exactly 3 intervals, so you cannot pack more than 1/3 of active transmission. You reach that if, well, your ratio lambda over mu, so the access intensity of the protocol, the ratio between the mean transmission time and the inverse of the mean backoff time. So if you have backoffs which are very short and transmissions which are very long, well, you will reach to something which is ideally, which maximizes the spatial reuse. And indeed, if you increase this ratio, the spatial reuse will move from values which are pretty far from 0.33 to something which is ideal. But of course, the cost of that is that if you have a linear network, well, the nodes which have few neighbors will tend to take the advantage, and this advantage will propagate through the whole network. So this spatial reuse comes at the cost of fairness. Unless you have a perfectly regular topology, like a circle. So if I arrange all the nodes in a circle, then making the protocol more aggressive by giving nodes a short backoff value and a long transmission time, simply increases the spatial reuse exactly as above. But since all links are exactly equal, the fairness remains the same. Of course, what is hidden here is the fact that for shifting from one independent set to another independent set, the time will be extremely long to shift between one of the two. But what I would like to focus more particularly is the topology. So what happens in 2D? So in one dimension, if you take a finite value lambda over mu, well, if you take a large network, boundary conditions here will affect here on the line, I have all the links, and this is the proportion of time each link is active. And so here, the link which is at the border has the competition with only one neighbor, so we will actually benefit a lot from the competition, and that advantage propagates but fades away in the middle of the network. And actually here, the boundary conditions do have an impact on what happens in the middle of the network, but that impact fades away as I go in the network. And so essentially I don't feel any difference. In the two-dimensional case, things are more interesting. In this case, instead of having intervals which are packed on the line, each active transmission will consume a footprint, which in this case is a two-dimensional footprint. So I have nodes which are arranged here on a square lattice. And when a sender wants to transmit a packet to a destination, well, this link will be active, and it will inhibit all the other links that are in competition with this link to be active simultaneously, as well as a number of links here. And so essentially it amounts to pack this kind of hexagons on the grid. And so you have different maximal independent sets. Actually you have you have 4 which are for translation of horizontally active links, and 4 which are translated versions of vertically active links. And so in this case, actually border effects are much more important, actually due to a phase transition. So if you look at what happens first, sure. The mixture, all the.
There is no picture.
Sorry? No, but this is like the maximal packing. Of course, they will all be the same direction. But of course, so I have a lattice. That's a good question, in which any links can be active, and so the maximal spatial reuse will be used. So you will get that either with only vertical links or horizontally links. But of course, you start with a network, and you will. I mean, it will reach often states like this. But it's a different context. So for the one-dimensional lattice, just observing what the effect of size will have on the network, it's interesting to compare what happened in 1D versus what happened in 2D. So I take exactly the same size for the network. I just increase the size in 1 dimension or in 2 dimension, having here a 1-dimensional lattice or there a 2-dimensional lattice. So in 1 dimension, essentially what I have is that the spatial reuse, as we have seen before, increases with the ratio lambda over mu. Actually, we can compute this curve explicitly in 1 dimension. There are different techniques of doing that, and the spatial reuse increases to reach 1 over 33 as lambda over mu increases. And there's very little difference between the two. The difference is just due to the boundary effect, that some nodes at the boundary have fewer contenders, and that gives them a little margin. The fairness index decreases as the spatial reuses increases. It decreases faster if the boundary conditions, if I have a small topology, because the boundary conditions are closed, so it affects very quickly all the links. And the red curves here will go down later on, simply because I have a larger lattice, so it takes actually larger values of the ratio lambda over mu to have the influence of what happens at the boundary perceived of what happens inside the network. If I take a 2-dimensional lattice, I have roughly the same thing, at least for what is in green. At least for the small value, you see that the spatial reuse increases with the ratio lambda over mu for exactly the same reason. I cannot compute this curve anymore, but I still have an increase. But you see, of course, the spatial reuse increases much more sharply at some finite value lambda over mu just here. And the fairness index, it's even more dramatic. If I take a large lattice, I suddenly have that the fairness index just decreases suddenly for some finite value lambda over mu. And so I get something which is extremely unfair. And the reason for that is that we have here the evidence quite obvious of a phase transition taking place. And so for using that, I need tools from Markov random fields, so give measures. So remember here that for a loss network model, on a finite network, the probability to have an independent set or a pattern or configuration, if I speak here in the area of Markov random field, x with n of x active link is simply given by this expression where z is the partition function, is a normalizing constant. I just extend that graph to an infinite network, and so this definition here does not apply well because the constant would be infinite. So I need to go via Gibbs measure. So I take first a finite subset of nodes, and I take as delta B the set of nodes that are not in B but adjacent, so the boundary of that particular set of B. And I take x of B, the configuration x restricted to the nodes on B, and similarly x of delta B, the configuration of x on the boundary itself. And so I can specify there properly the conditional probability to have the configuration x on B, given that I know the configuration on its boundary, exactly by extension of this formula. Here I have added explicitly the fact that, of course, I need to have that the configurations on the two need to agree. So I have one if the boundary conditions and the particular configuration I observe in B is feasible, and 0 otherwise. A measure which is a solution for this for all finite sets of nodes B and all prescribed conditional distribution is a Gibbs measure. It can be viewed also, so another way to view it is to construct it as the limit of a finite volume Gibbs distribution with randomly chosen boundary condition, and when you increase B to the entire graph. And the interesting thing here is that there might be multiple measure, infinite volume measure pi, that verify that solution, or there can be only one. Now here it's a model which actually is well known in physics. It's nothing actually, when you think of it, it's a natural model. It's called a hardcore model, but the model which is studied in physics assume actually very simple interaction compared to ours. Essentially, a hardcore model is a model in which each side of the lattice is occupied or not by an atom, with the restriction that if a side is occupied by an atom, then its 4 neighboring sides cannot be occupied at the same time. So I have an exclusion region. Here it's exactly the same, and so here I have only 2 phases, essentially. Here I have exactly the same. I have, if a link is active, that's the footprint around the link, then actually I have a number of links which cannot be active simultaneously, so it's a hardcore model, but the number of links and the number of hexagons which surround it is much larger. If I look at the contention graph, whenever I have one, so these nodes here represent a link. It's the contention graph is not the graph with the nodes. So when this link is active, all the other links must be silent in order to have a transmission due to the carry sensing mechanism. And so in this case, actually, I have many more phases, and so the phase transition is more difficult to obtain. Now, in one dimension, there is only one Gibbs measure. That's relatively easy to show. In 2 dimensions, we can have one or more multiple measures. Essentially, when I should have put that early on. So if I have finite value, lambda over mu, which is small enough, you see that this is the distribution of the probability that a link is active. And you see that you have something which is a fairly unimodal, probably close to Gaussian, around 1/8, because 1 link out of 8 can be active simultaneously in pattern of maximal spatial reuse. But if I take other value of lambda over mu, I have a few links which are active all the time, and most of the links which are never active, which is the symbol of and the evidence of a phase transition. And actually what we could prove, but again this should be certainly much strengthened, is that there are 2 finite values for sure for which we have a unique Gibbs measure if the ratio lambda over mu is small enough, and for which we have multiple Gibbs measure if we're large enough. Now we can suspect that, of course, it's the same value here. The proof, the first part, it's an easy proof once we can use these results. The second part is a very tedious proof, even if the idea is using only the classical pulse argument, because there is a lot of so the contour removal that you apply when you use pulse argument uses a lot of flipping rotations and so on of all these hexagons. And so there what we did is simply to initialize the process so that we can an iterative process that can make use of a previous work by Hellman in 1974. I will just describe here the first part of the proof, so the fact that there is a unique Gibbs measure, because that's something that uses percolation, and more precisely disagreement percolation. So the method is as follows. So it has been proposed by Vandenberg, Maas, and Steiff in a couple of papers. So we take 2 Markov random field, pi prime, with the same specifications. And we draw 2 realization of this Markov field according to pi and pi prime. So more precisely, we pick the same value for the boundary conditions, and we look at the measure when we have the same specification. So it's a function of x and x hat. Here the specification is of course given by the expression that we have for the hardcore loss model inside the box P. And a path of disagreement for these coupled fields is a path where we have a different value for x and x prime for every node on the path. And so that's what we define as a path disagreement. And the theorem is as follows, that if I look at the product measure that x prime has an infinite path of the disagreement, if this is equal to 0, then the 2 measures must be identical, and so there is a unique Gibbs measure. So to put that in a side percolation framework, well, you will simply take the sup of this quantity for all possible pattern or configuration xx prime and for all possible indices, call this P, and put that in an independent site percolation model with open site probability P given by this. And if that model is subcritical, then there is a unique Gibbs measure. And so the big advantage of that is that instead of having to do many computation, we simply have to compute that condition here. So we take we take exactly this specification here. I do that actually in the next slide. So I consider the probability that under the product measure the value of xi and xi prime differ, given that they're exactly the same on the boundary of that vertex here. So here I take one node, I. This is the boundary of that node. These are all the nodes which actually which would interfere with the link here, all the links which would interfere with that link here. And so I can compute that explicitly because I know the specification. Actually, the result is easy. If any one of these other vertices representing contending links is active, then this link cannot be active, so the result here must be 0. And if all of them are silent, then this node is able to transmit. It is willing to transmit. Well, in this case, since I've blocked all the value of all the other nodes, I have a two-state Markov chain. It is willing to transmit with a probability lambda or lambda plus mu, because I simply have a continuous time Markov chain with rate lambda of transmitting, mu of stop. So that's the only value which I have. So the site, the value here is simply lambda over lambda plus mu. I simply replace this in this expression here. And so if I know the site percolation threshold on this graph, which contrary to this morning, I don't think we know explicitly, but which is non-zero, then if the value of lambda over lambda plus mu is less than the dependent site threshold on this graph, I know that I leave one Gibbs measure, and so I know that I am in an area where I have fairness, at least in the long term. I have a unique Gibbs measure here. Let's see what it gives on some simulation also with varying topologies. So remember, this fairness index indicates how far we are from the uniform distribution. And so there are two things that I can affect. So that what I explained so far was only on lattice, on regular lattice. So if you perturb a little bit, the lattice might be interesting to see what happens. On the lattice, the advantage is that it's a topology which is extremely fair, because the only source for unfairness that we have seen before is this phase transition that takes place in the loss network model, and that affects, or the hardcore model, and that affects the contention, but there is no topological unfairness. Of course, if you take a random graph which has varying node degree, then there's a first source of unfairness, is the fact that some nodes have many contenders around them, whereas other nodes have almost no contender around them. And so there, of course, for low value even of lambda over mu, where the lattice would be still perfectly fair, well, your random graph will be already unfair. And actually, you can compute, I mean, that's a simple computation, that the fairness index, if you expand this expression in series, will be 1, of course, that's the ideal case, and the first negative term of the series will be proportional to the variance of the node degree of the contention graph. And so if you're on a lattice, well, you have something which is perfectly flat. If, of course, you have something which has already a very highly variable node degree, well, then you will lose a little bit of fairness. And so if you plot the curve, for example, for a pure random graph with a random contention graph, you will have a curve that decreases like this, so gently, and so here already it decreased because of the variance. And the closer you are to a perfectly regular lattice, the closer you will be from something that starts very flat, but then that has this phase transition taking place. So there are really two sources of unfairness which are kind of blurred in near-regular topology. The first one is something which is local, and that's why you have the variance of the node degree that comes into play. It's just the number of contender you have just in your local neighborhood. And then the second one that comes irrespectively of the topology, but is a phase transition. Sorry, I shouldn't say irrespectively of topology. That comes even for regular topology, is that for large value of lambda over mu, then you have a phase transition, and so this is linked to, at least to be on the conservative side, to a quantity which represents a global property of the graph, which such as the side percolation threshold of the contention graph, and so no longer a local property.
So,
yes?
Sorry, you said that for arbitrary situation, you always have phase transition when lambda divided on mu is.
No,
It's not true.
No. I said it's on the so for large value of mu on regular lattice, I should say.
Yes, on regular lattices, it's not always true. For example, if you consider square lattice, and if you consider that your
Yes. No. I mean. So in the hexagonal model, I have. Yeah. I mean, I should say here. Yeah. I cannot conclude anything for this part here. But if you don't have, so if you have the square, so the square lattice, but not the contention graph, and that is a square lattice.
For square lattice, if you decide that your edge has only, if you consider any edges which not connected with each other, if you include these configurations in your model, then by Lieb result you shall have that this Gibbs field has no phase transition. It's not trivial result, but it's true. So it's only for your special.
Yeah. No, I agree. Yeah, I agree. I mean, that's. Yeah, I would say it's only on regular graph that.
Regular graph, but not always.
Okay, maybe before switch, I don't know if there is other question before I switch to the other part. If not, okay, then I will move to the non-saturated case and some of the results that we have on that one. So here, remember, I will have exactly the same kind of protocol, but with one saturated source and all the other nodes which are relays. So in this case, well, what will happen is that I transmit a packet at the beginning very regularly, but after some time I will have again some competition between the different nodes. And so if the source transmits a packet regularly, the other nodes here will again benefit from a maximal special use if the backoff is very aggressive. And the problem in this case is that as transmission takes place, well, this node, typically the second node of the chain, is blocked by either transmission on the left or in its right, so will not transmit, and the other node will continue transmitting each time, and this situation will continue with, as a result, the fact that the Q of the first node will have a tendency to grow indefinitely as time passes. And so here we are going to take a discrete time Markov chain model. So we change of model as before, and essentially the model is as follows. I explain it here for 3 hops because the situation is more interesting about the transition between 3 and 4 hops. So the states are the queues. So the buffers of the queues of the 2 relay nodes. The destination, of course, absorbs directly the packets, and the source is saturated. And then I have 3 links, and I represent the state of each of the links by variable x0, x1, x2, which is just 0, 1, whether the link is transmitted at slot n or not. a slot corresponds to the successful transmission of one packet by any of these nodes. And the model is as follows. It depends on which, so what is the queue of the two intermediate nodes. So if the two relays here are empty, well, the only transmission that can take place in the next slot is, of course, the transmission between the source and the destination. The second one situation is when the queue of the first node here contains at least a packet, the other one is empty. In this case, either this node wins the contention, wins as the shortest backoff, or this the source wins. And so with probability 1/2, it is the first link which is active. With probability 1/2, it is the second link which is active. Same thing for the situation where I have only the second queue here, which contains a packet and the source. In this case, either the second node wins the contention and so has a shorter backoff and so transmit the packet, or the source transmit the packet. And finally, when all queues contain a packet, then these three nodes are in competition, and each of them has a probability 1/3 of winning the channel at this slot. And so at step n, you pick a pattern according to this discrete Markov chain, and you simply update the state of the buffer depending on which transmission takes place. And so this defines a very simple random walk on the plane B1, B2, and it's a random walk which actually has been studied before. It's a Markov chain which is non-ergodic, and so it's unstable already for 3 hops. For 4 hops, if I extend the algorithm, it would be exactly the same. And so it would show that these algorithms are unstable, so the queue here indeed will go to infinity. And indeed, in theory, that's what happened. But since there are only 3 nodes, we could verify that in reality, and in reality, it does not grow to infinity. So we have something.
So it's not ergodic, or it's transient? Not ergodic.
It's not ergodic.
Either non-recurrent or
I think it's non-recurrent.
non-recurrent.
Yeah. It's not transient. And so the queue size here is, but in practice, this is not seen. So otherwise, you would have that the queue size of the first node would saturate very quickly. So clearly, it means that the model is not sufficient. And to see why the model is not sufficient, it's because we have assumed so far that the exchange RTS-CTS was taking place instantaneously. So that immediately a node know whether its neighbor is transmitting or not. That never occurs in reality because you have some time which is spent in the transmission of these RTS and CTS packets. And so when, for example, in this situation, the backoff at node 2 is the first one to expire, well, then node 2 transmits its packet to node 3, but node 1 doesn't have any problem, because it wouldn't have any packet to transmit anyway. The problem occurs when the backoff of node 0, so the source, is the first one to expire. In this case, if I assume a perfect exchange of the information that node 0 is transmitting, all the other nodes 1 and 2, 1 will receive the packet and 2 instantaneously will refrain from transmitting anything. And so there is no problem. The source will transmit its packet to the first node here. But in reality, the backoff of node 0 might expire so at step n. The transmission takes place, but node 2 will take some time to be informed that this transmission takes place. Or even worse, the RTS-CTS options might not be turned on, and in this case, node 2 will not know that the source 0 is transferring. So the backoff of node 2 might expire slightly after, and node 2 might still want to transmit its packet, or just the RTS. In this case, of course, packet 2 will collide with the packet from node 0, and so there is a collision, and this transmission is aborted. But the transmission from node 2 to node 3 takes place. This transmission is not affected by the collision that just takes place here. And so we call this a stealing effect because even though the competition based only on backoff was won by source 0, the downstream node, even if it transmits a little bit later on, can still grab the channel, steal the channel from the legitimate winner of the competition, which would be node 0. So this transmission takes place compared to this one here, and that happens typically when there is some delay between sensing between the time at which node 2 senses that there is indeed a transmission here and decides actually to transmit a packet. So in reality, this happens quite often. Now, what has that as an effect? If we call P, we model by P the probability that I steal a channel for downstream node. Well, it changes just slightly this random walk by changing a little bit these probabilities here, but in the good direction, because you see that I reduce the number of time I go to the right by 1 minus P. Actually, this effect flushes packets which are in the downstream nodes much further from the network, and so it will have a stabilizing effect. And so if you do that, indeed, with this model here, you can prove that the Markov chain is ergodic as soon as you have a stealing effect, which is present, so as soon as P is strictly above 0. So that's why I suspect that it's non-recurrent for P is equal to 0. And actually, there's recent work which has been shown to actually give the full distribution of this Markov chain, which is a non-product form in general. Now, unfortunately, for n is equal to 4, even though we have the stealing effect, the network is unstable. So you win for 3 hops. For 4 hops, it is unstable, and so it's again using the Lyapunov function methods that we can prove that. And here, experimentally, the results of the experiments coincide with the model. Indeed, if you run the experiments with 4 hops, you see that the queue of the first relay just saturates. Since there is a hard limit at 50 packets here, the limit is indeed reached at 50 packets just here. And looking at some other works made by our colleagues in Basel, typically you will see that very often mesh networks with more than 4 hops are not that frequent. No, there might be many reasons on top because people run TCP routing and so on. So it's hidden, but there is a fundamental reason, is that the protocol has an instability at the medium access control layer already. Then, of course, anything that runs on top of this will have a severe problem running directly. And so this is using the real 802.11 protocol, even though the model is extremely simplified compared to the simple situation. So how to fix that? That's something we are doing now. Well, essentially the situation is not so bad, so we call that easy flow. So essentially what we would like to do, remember, is to change as little things as possible and not use message passing. And the two are actually possible. You can still use the same kind of protocol simply by playing with this ratio lambda over mu. In practice, is the contention window that is called, by a node depending on the successor before occupancy. So typically, you would implement some form of a back pressure there. And why is it possible to do that? Because you have here, and so that's what we call our buffer occupancy estimator. You can estimate easily the occupancy of the queue of the next hop, simply because all the packets that are received by the next hop have transited via your node. So essentially, you know all the packets that will be transmitted later on by the next hop. And since you have a wireless channel which broadcasts this information, you simply listen when a packet is transmitted, say, from the green to the red. This packet has gone through the blue, so the blue knows exactly which packet to wait for the transmission, and there you estimate very precisely what is the queue size. And actually it's extremely precise because the estimation takes place at the time of transmission. So even if you have something which is extremely time varying, the transmission is extremely the estimation is extremely precise because you have the most recent information of that, message passing might have some stale information. And then you adapt the contention window. So far we have only an additive, so we have a mechanism typically of additive increase and additive decrease, actually not multiplicative decrease, for this adaptation. And so if you play that on the 4 hops, after some tangent, usually it gives pretty good results, but of course here we have no analytical result except that it stabilizes the network, but we don't know how far we are from throughput optimality. So let me reach some conclusion. First, for the saturated network. So here, the model we have used, and actually has been used already before, it's the loss network model, which is a continuous time Markov chain. We have looked at, there are quite a few differences with 802.11, which are reported in this paper, but it gives a fairly good sense of what happens. It explains why, without collision, so it's something that you wouldn't have experimentally, but only on simulation, starvation is a price to pay for maximal spatial reuse. It's something which is inherent to all these protocols. But by playing on this ratio lambda over mu, you can easily trade off spatial reuse and fairness by just playing on this quantity here. What I didn't mention is actually what happens with asymmetric exclusion domains. So typically when you can hear the transmission that takes place at a range much further than the range at which nodes are silent because of a transmission, that actually mitigates unfairness, but we do not have a reversible Markov chain as before. And because so it's much more difficult to analyze, but actually it has some virtue which I don't have. Now on lattices, so phase transition make it stronger at high activity. What I didn't mention at all is short-term fairness. And then also how to play with that. So essentially the fact that CSMA naturally finds maximal independent set for you is an advantage if you could switch from one of these maximal independent set to the other in order to ensure some fairness between the different nodes that are active at some point. And so how to do this? So recently we have some result on some self-synchronization without message passing using this kind of scheme, but how to combine this ability of a carry sensing mechanism to find maximal independent sets with a fair rotation between them. Of course, that would be something that would be at the same time fair, and a protocol that would be at the same time fair and spatially efficient. In the non-saturated case, but it's only one particular scenario, so one saturated source, we have a discrete time Markov chain, and there we need to introduce this stealing effect, which actually happens in reality and which helps to stabilize the system. And so it's still unstable for n is equal to 4. Of course, open questions is typically what happens for other topologies or for larger value of n. So we can actually trade off, so the minimize the delay simply by implementing some form of back pressure without message passing, just based on the estimated Q size of the downstream node, thanks to the broadcast nature of the wireless network. There, of course, the question is for the easy flow, how far we are from throughput optimality, so that we don't know at all. And more theoretically, it's also how we could justify this discrete time Markov chain. We have put that model as such without justification other than it fits the experiments. But I mean, it's the way we nodes contend with each other on the 3-hop or 4-hops chain can work. On the longer chain where these decisions will be different from one part of the network to the other might turn out to be very wrong. And so I think I'll stop here.
You mentioned in the previous slide local fairness. Or
Short-term fairness, okay. Short-term fairness, okay. Long-term fairness, that's, so if you take the best example would be probably the circle. So the circle you have only, so every node has exactly the same neighbors. It's long-term fair even if you take access intensity which are very high. But the time to switch from one maximal independent set to the other maximal independent set can be extremely long. So it's long-term fair, but short-term you might wait exponentially an exponentially long time before switching from one to the other. So how to characterize this? Even if it is long-term fair, can we characterize the short-term fairness? Exactly. We have we have some results on that, but actually it's a random walk on the triangular lattice, but with very ugly boundary conditions. It's like the Gamble rune problem would be that you travel on your random walk, you absorb by one edge, and then you continue with the two. But here, you rebounds from the edge inside the triangle, and it makes it empty. But Olivier has has some good results on that. But,
so in the line network case, why can't you just tell the source to transmit in every third slot and you're done?
We have done that. So throttling the source, but the difficulty is to know at which rate you want to. So if you do one every third one, if you know exactly the number of hops, then yes, you have a TDMA.
It doesn't even matter. The number of slots, the number of hops wouldn't matter. No?
If you know that you have exactly 3, but that would be only valid if you have 2 flows, for example, or 3 flows together. You will need to also maintain some fairness between different flows, and then you get back closer to a TDMA schedule instead of a purely CSM.
Okay, but I thought here you have one source and one flow, and you.
Yeah, I didn't show. Okay, the results, the analytical results we have, but the experimental results we run the same protocol, of course, with multiple flows originating at different nodes, because otherwise the restriction would be too strong. It's a good point. Otherwise, the restriction would be too strong on that particular scenario only compared to the other. Take it more because it's more like a kind of the simplest example on which this can be worked out. But of course, the intention. So the other experiments we have that starting. So you take a network with a tree topology or general topology, and then you run the same protocol with different sources at the same time. But there, I don't have any model to present to try to get the results.
More questions, comments?
In the case where you would have randomness in the location of nodes, and if you would have the extra randomness that would come from taking interference into account.
Yes.
And because here, I mean, interference is just
it's
just, I mean, the sort of exclusion domain, but the wireless medium is really additive. So if you would mix these two type of randomness, so would you expect this phenomena to persist or to vanish, or?
Usually, the more different source of independent source of randomness, the better it helps. I mean, so when I was mentioning the difference between the regular graph and the graph with varying node degree, we see that with varying node degree, things are perturbed already much more. If we have, for example, asymmetric exclusion domain, it mixes things much better. So if you introduce noise due to inference, I think it creates mixing that helps a lot. It should help a lot in the fairness. So any perturbation helps actually.
Okay. More questions? Doesn't seem the case. Good, thanks.
Thank you.